I'm Anil Kumar. Welcome to my series on rational functions. We'll discuss reciprocal functions in this particular video. These are the topics which we are going to touch upon. What are rational functions? Functions versus reciprocal functions, vertical asymptotes and horizontal asymptotes. We'll sketch graph of reciprocal functions and have some practice test examples. Now let's begin with what are rational functions. Let us say r of x is a rational function. Then it is always represented as a ratio of two functions, two polynomial functions. We can write n of x in the numerator and denominator as d of x. Now it is basically quotient of two polynomial functions. You can say quotient of two polynomial functions. Now, of course, denominator cannot be 0, and therefore we do have a restriction that d of x is not equal to 0. Correct? So in every rational function, we do have a restriction. Now, sometimes you could have rational functions without restriction also. We'll take up some examples to illustrate. Now, when I say d of x is not equal to 0, that means rational functions could have restrictions. Since the denominator cannot be equal to 0. As we explore further, these restrictions will be reflected on a graph as asymptotes. So these restrictions could be vertical asymptotes or holes in the graph of a rational function. So I'm giving you a heads up on few topics which we are going to see later in this particular video, right? So to summarize, rational functions are basically ratios of two polynomials where the denominator cannot be 0. If denominator is 0, it leads to restrictions on a graph that could be a vertical asymptote. Sometimes it could be a hole also. Now, a hole has a special property that we have a common factor between numerator and denominator. We'll get into that details later. Correct? So with that, let's now take up rational functions of the type which we are saying reciprocal functions, right? So, as you know, n of x, the numerator, could also be 1. So, if the numerator is 1, right, so if n of x equals to 1, that is numerator is 1, then we have a rational function of the form 1 over d of x. Now, this 1 over d of x is reciprocal function. Is reciprocal of the function d of x. Do you get the idea, right? So that is what a reciprocal function is. So we'll explore this reciprocal function in greater details now. Now let's discuss functions and how reciprocal functions are related with functions. So as we were saying, let's get back to rational functions. Rational functions are basically ratios of two polynomial functions. We are calling them n of x and d of x simply because it's in the numerator and one is in the denominator, right? However, you should remember that both of them are polynomials. And here we do have a restriction that denominator can never be equal to 0. So that leads to restrictions. Now, what are reciprocal functions? Let's talk about reciprocal functions. If f of x is a function, then what is the reciprocal of f of x? Of f of x will be actually equal to 1 over f of x. That is what reciprocal is. Now, f of x, if it is a polynomial, then f of x has no restriction. However, as soon as you write 1 over f of x, we have to write the condition that now f of x is not equal to 0 because it is in the denominator, right? So reciprocal of f of x is indeed 1 over f of x. That is what reciprocal function is. So, for example, if I have a line, let us say if f of x is equal to, let us say 2x plus 1, then 1 over f of x will be equal to 1 over 2x plus 1. Clear? Let us say if we have another function g of x, which is, let's say, x squared minus 1, then 1 over g of x will be equal to 1 over x squared minus 1. Now, whenever you write these functions, you have to be clear that for the reciprocal function, we'll have a restriction. Here, x is not equal to minus half. And in this case, x is not equal to plus and minus 1. You get an idea. So a reciprocal function, as shown here, can have restrictions even though the function has no restriction, right? So as far as the function is concerned, we can write here x belongs to all real numbers, right? In both the cases. There are no restrictions. However, the reciprocal has restrictions, right? Now, let's talk about general numbers and see how values change when we do reciprocal of something, right? So what I will do here is I'll take up some examples. So let us say that we'll just have some numbers x, where x belongs to real numbers. Then what happened to 1 over x? That is what we will check, right? If the value of x is, let us say, 1, then the reciprocal is also 1. If the value of x is minus 1, the reciprocal is minus 1. So we see that for x and its reciprocal, the values do not change if x is plus minus 1. We call that as invariant, right? So they don't vary. So this is called invariant. They do not change. Perfect. So as the name says. Now, if I have a value 0 for x, then here it becomes 1 over 0, which is not defined. Correct? If x is any negative value, any negative number, then 1 over x is also negative. If x is a positive number, 1 over x is always positive. Clear? For 0, it may not be defined, but for negative, reciprocal is negative. For positive, reciprocal is positive. Now, if x value is increasing, let's say going from 1 to 2, then 1 over x will go from 1 to half. It will be decreasing. And if x value is decreasing, then 1 over x will be increasing. Is that clear? Correct? So these are some very, very important things to consider. One more thing which you should do is, what happens when x is approaching infinity. A very, very large number. In that case, 1 over x will approach 0, correct? So this is very important to understand. So if x is approaching infinity, 1 over x is approaching 1 over infinity, correct? So we'll take help of these properties of reciprocal of the number itself and then sketch some reciprocal functions. Does this sound good? Okay, let us see. So before we get into sketching, we'll talk about asymptotes, vertical and horizontal asymptotes. Now, let me sketch a graph. So I'll begin with graph of a straight line. Let us say the equation of this line is y equals to, let's say 2x minus 1. Okay, let's say 2x minus 1 is the graph which I'm going to plot. 2x minus 1 really means that the y-intercept is going to be minus 1 and it'll go 2 up and 1 right, correct? So that is how it is going to be, 2 up and 1 right. So y-intercept is here, 2 up and 1 right. So the graph of this line will be kind of like this. Let's say this is a straight line we're talking about. Now this point is minus 1 here and this point is half, correct? If I write x equals to half, we get that point. Now in this particular example, what we see is that at half, y equals to 2x minus 1 is 0, right? So what I will do here is kind of make a table and fill this up with some values for different values of x, right? For different values of x. So let's say we'll take some x values. Now, if I write x as equal to, let's say 0, in that case y equals to 2x minus 1 is minus 1, and if I write x as half, in that case y is equal to 0, and if x is 1, in that case it is 2 minus 1, which is 1, and for x equals to 2 we have a value here 4 minus 1, which is 3. For the negative values, if I take minus 1, then it gets me minus 3, so that becomes negative. Now, if x value is very large, less approaching infinity, then this value also approaches infinity, right? Now let us consider the reciprocal of this function, which is 1 over 2x minus 1, right? So which is the reciprocal function. In that case, the values will be reciprocal of these. So we'll have minus 1 over 3. This will be minus 1. This does not exist. 1 over 0 is not defined. This will be 1. This will be 1 over 3. And infinitely large will approach 0, right? So basically we should write approaching infinity will approach 0. Now here you can see that we do have invariant points as minus 1 and plus 1. So these points will be common for, let's say this is 1 for us, right? So at 1 it is 1. Let's say these are invariant points represented by these 2 points. Now as the value of x increases, that is to say this is x, let us say, as it increases, we see that the reciprocal value actually decreases, right? So on this side the graph will be kind of like this, approaching towards 0. As we move to the left of 1 towards 0, positive side only towards this point, it actually increases kind of like this. So you can take up more values to fill this up. On this point itself, which is half, we know it is not defined. Since we have written here does not exist, that means does not exist means not defined. So actually speaking, we have a vertical asymptote at this point. So this is at x equals to half, right? On the left side of this vertical asymptote, the graph of the curve will be kind of like this. It crosses at -1, right? And goes down. And on this side, it will go towards the 0. As x approaches -infinity, reciprocal approaches 0. So that is how you're going to get the graph of this line. Now from here, we will define two values, rather two important characteristics. One is the vertical asymptote. So what you note here is that as x approaches half, the y value, let's call this function as g of x, right? Then g of x approaches infinitely large value. Now you will note that if you are on the right side, that means when you approach from the right side, g of x approaches positive infinity. However, when you approach x from the left side, we write like this. That negative on the top means approaching from the left side. Then the reciprocal function g of x approaches negative infinity. This is negative infinity. You get the idea, right? So this graph is of g of x, which is reciprocal of the linear function. Now, if you are approaching a value in the between for x, and if the y value is approaching infinity, we call this as a vertical asymptote. Is that clear? On the other hand, what we note is that when x approaches large value, positive infinity, or when x approaches large negative value on the left side, g of x approaches 0, right? Both sides. When it is positive, g of x is 0, but from positive side, from above. That is from above, right? And here minus means approaching 0 from below, right? Approaching 0 from below. That is the significance of those plus and minus signs. So but it is approaching a value, right? It is approaching a value, and this is what we call horizontal asymptote. Now each can be written in the form of an equation. So in this particular case, the vertical asymptote is x equals to half. Since when you approach half, then the function value approaches infinity, and the horizontal asymptote is the value which the function approaches, which is 0 in this case. So we say y is equals to 0 is horizontal asymptote, and x equals to half is vertical asymptote. Is that clear? So that is how we understand horizontal and vertical asymptote. Now in this graph, you also see once again that we do have invariant points, right? So we have invariant points at which are these, right? Plus and minus 1. Do you see that? Y value being 1 or minus 1. Whenever the graph of the function is positive, reciprocal is positive. When the graph is negative, reciprocal is negative. When it at the x-intercept, we have a vertical asymptote. And as x approaches infinitely large value, the g of x value approaches horizontal asymptote, which we are now showing in the form of this dotted line. It is never there. Do you get the idea? Now, From all this, we can write what is domain of g of x, the reciprocal function. Domain of g of x is x belongs to real numbers, but x is not equal to half, which is the vertical asymptote. And what is the range? Range of g of x is y belongs to real numbers, but y is not equal to 0, the horizontal asymptote. Do you see how domain and range and horizontal and vertical asymptotes are related? That's kind of important to understand. Now with that knowledge, let's move on and understand how to sketch graphs for reciprocal functions. We'll take all possible examples which you're going to consider in this advanced functions curriculum. Now we are going to sketch graph of reciprocal functions. Your test actually starts from now, so treat this as a part of test, right? So what you need to do here is that you need to pause the video, you need to sketch graph of reciprocal function, that's the first part, and the second part which you have to do is to write domain and range of reciprocal functions. Correct? So that is your test. Here I will just sketch some graphs. Let's begin with a straight line. Then we'll take up a parabola. Then we'll take up a cubic function, right? So let's draw these three first. So this time I'll take a line with negative slope, a parabola, let's say like this. A cubic function, let me make it, okay, let's make it like this only, a basic cubic function. Now let us see how to sketch reciprocal of these functions. The idea here is, first step, to mark the values where the function is 1, right? So let us say for each, this is 1 for us. Let's say this is 1 for us. So that will be minus 1. Let's say this is minus 1. Okay. Now, those 1 and minus 1 will give us invariant points. Let's figure out where are those invariant points. So, y value of 1 here and minus 1, those are invariant points. In this case, we have these two invariant points, and here let's consider the vertex itself at, let's say, minus 1. The invariant points here will be these two. So these are invariant, they are common to both. So we are sketching 1 over f of x, the reciprocal function, for all these graphs in red. Now how about x-intercepts? These x-intercepts will translate into vertical asymptotes. So sketch vertical asymptotes for each x-intercept. Okay, so we have this vertical asymptote. Okay, so in this case, y-axis becomes vertical asymptote. Perfect. Now, as you know, for positive part, it is going to be positive. For negative, the function is going to be negative. Now, in our case, let us say the minimum value of the function is minus 1. Let's think this is kind of like this. Let's say this is a parabola where these points are minus 1 and plus 1. So at 0 we have the vertex. Okay, let's assume that. It doesn't look like, but still. Now, the graph of reciprocal will be more or less like 1 over x. Now this positive half will be kind of positive half, but Vertical asymptote, as you can see, so it is going to be kind of like this, approaching 0 and approaching the vertical asymptote. So on this side, kind of like this. Do you see that? Negative all throughout, invariant point -1, and approaching 0. So here, in each graph, write down what is equation of horizontal asymptote and what is the equation of vertical asymptote. Let this be also part of your test, right? So we have question 1, 2, 3, and 4. For the first one, horizontal asymptote is y equals to 0. Vertical asymptote is at, let me call this point as, let's say half. Is it okay? Okay, so vertical asymptote is at x equals to half. For the second graph, let's first sketch it. These are invariant points, so the graph will be kind of like this, positive half. So make it like a reciprocal function 1 over x. Now reciprocal of -1 is -1, so here it is going to turn like this. Does it make sense? Now -1, that means the graph will be kind of like this, positive 1, so it will be kind of like this. Shape is more or less like 1 over x. Now let's write down the horizontal and vertical asymptotes. Here again, y equals to 0 is your horizontal asymptote. Here also, y equals to 0 is your horizontal asymptote. The vertical asymptote, we have two in this case. One is at x equals to -1, the other one is at +1. Here, as far as the vertical asymptote is concerned, we have just one, which is at x equals to 0, right? So vertical asymptote at x equals to 0. So I hope all this is absolutely clear. So in first phase, you have learned how to sketch graph of a reciprocal function, how to write its domain range, and also equation for horizontal and vertical asymptotes. Now I'll take up few more examples, and with those examples, we'll explore more characteristics of reciprocal functions. So let me take 3 more. Now these 3 are very typical. One is semicircle. Semicircle is a function, right? Let us say this point here is at -4 and this is at 4, okay? And this will definitely be at 4. You have to sketch graph of this function. Now let me take another very important function, and this time I'll sketch this as 1 over x square graph, kind of like this. Oh, so that is a graph, and you have to sketch reciprocal of this graph. Is it clear? Okay. The last one here, I want to sketch like this. A parabola facing downwards, where this point here is at half. Now here we'll assume this point to be at, let us say, 2. And those points are already given to us, right? So somewhere here the value will be 1, right? Okay. Now somewhere here we have -1, and of course 1 on the other hand. I would like you to pause the video, sketch graph of these functions, graph of reciprocal of these functions, and then write down domain, range, and more than that, I would like you to write down interval where 1 over f of x is increasing or decreasing. Interval also where it is positive and where it is negative. So these are additional features which you have to look into for rational functions and also reciprocal functions. So take your time to first sketch and then describe. This is part of your test. Okay. Now, after the sketching, I'll give you a link for objective type multiple choice questions on reciprocal functions, which will help you understand all the concepts about reciprocal functions. Now let's quickly sketch the reciprocal of these functions, right? So I'm sketching 1 over f of x. Now, if this is 4, somewhere here will be 1. So the invariant point is kind of here. Now we have a vertical asymptote at 0. So at the end of this semicircle, we are going to have the vertical asymptotes. Inside part will go through these ones, and 1 over 4 will be the local minimum. So it is going to be kind of like this. Do you see that? Where this point here will be 1 over 4. So that means as far as the domain is concerned, the x value is between -4 and 4, and the y value is greater than equal to 1 over 4. Do you see that? In the second case, we do not have any vertical asymptote since there are no x-intercepts. When the function approaches 0, it is going to approach infinitely large f of x, 1 over f of x, the reciprocal. Reciprocal of 2 is half, so this point will be kind of here, right? Now, at 1, it is going to be crossing the graph. Now, what happens as it approaches 0? This is going to approach infinitely large value, correct? It's going to approach infinitely large value, correct? So from here, it's going to be like this, approaching infinitely large value. You'll also note that as this function is decreasing, reciprocal function will be increasing. So I hope you understand increasing, decreasing behavior of this function. As far as the domain is concerned, you can see that x belongs to real numbers, and as far as y is concerned, it is, this value is half, right? Greater than or equal to half. In the last case again, we do not have any vertical asymptote since there are no x-intercepts. Now in this case, reciprocal of half is 2, somewhere there. This is like -1. So here the graph will be kind of like this. Like this. Just reverse of this. I get my point? That is how the graph is going to look like. Now, in the third case, as clearly you can see, x belongs to real numbers and y is less than equal to, less than equal to this, which is 2 minus 2, right? I should say greater than or equal to -2 and less than equals to 0. It is never approaching 0. It's never at 0. It is approaching 0. Perfect. So that is how it is going to be. And now, from all these graphs, you can write vertical asymptotes also, right? So vertical asymptotes at -4 and +4, no vertical asymptote. So here, the vertical asymptote is at x equals to ±4. Here we have horizontal asymptote, which is y equals to 0, correct? But no vertical asymptotes in these two cases. Now, write down the interval for increasing and decreasing of reciprocal function. You can see in the last graph, for example, it is decreasing from -infinity to 0, but increases from 0 to infinity. So increasing from 0 to infinity and decreasing from -infinity to 0. As far as positive negative values are concerned, it is never positive, right? But it is always negative in the domain x belongs to real numbers. Do you see that? So I've answered all this for the last example. I'd like you to write the increasing decreasing intervals for these two graphs yourselves. You can put the answer in comments, and I'll highly appreciate if you have doubts, ask them. Feel free to ask your questions, post them. And if you like and subscribe my videos, that'll be great. And also look into the quiz, which is provided to you as an additional link along with this video. Thanks for your time and all the best.